Hi. Okay, so welcome to a kind of like a little off-topic mini lesson. One thing that I've talked about a lot in this class is that I'm not just trying to teach you chemistry, I'm trying to teach you how to be a good scientist, right? So one of the things that we're going to kind of dive into a little bit more in this unit is how do we plan and carry out our own investigations? And then from that investigation, how do we analyze and interpret all of the data that we've collected? In Unit 1, what we really were looking at was intro to chem lab. How do I be safe in the lab? What are some basic tools we're going to work with? All that kind of stuff. But what I want to do for this lesson is work a little bit backwards. We're going to learn how to plan and carry out investigations in class. I want to kind of start teaching you about the end goal for an investigation, which is the analyzing and interpreting data part of it. So I'm going to start here. We're going to backtrack in class together. So first off, when you're trying to analyze and interpret data, it's all about starting with what is your data, how are we recording it, how are we going to set it up to make something that actually is usable that we can then identify patterns from, right? So first thing we want to talk about is recording your data. We can use results tables to really help us organize our experiment in one table, record our data in it, record observations in it. So this is an example of a potential results table for some experiment that was run by a group of botanists, right? Within your data table, there's a lot of information you can pull out here. One of the things that you can pull out are variables. So essentially, a variable is anything that can change in an experiment. This isn't saying that these are all of the things that are changing. It's just that if I were getting ready to plan an experiment and I had all of these things set out in front of me, anything I could potentially pick to change is what I would call a variable. But there are three types of important variables that we have in any experiment. Your variable that is changed intentionally by you, the experimenter, in each trial is called the independent variable. And then any variable that's held constant then in experiment is called a control variable. So it is really important to note that if you are designing an experiment, you can't pick as many independent variables as you want. A valid experiment can only have one independent variable. Everything else must be a control. It must be a constant. It cannot change in each trial because otherwise you have no idea what the data you're collecting actually means. So consider the results table that's down here. If I take a look at the potential variables that this group wanted to build relationships between, they chose music type, light amount, water amount, plant type. So each of these things are potentials that they could have changed, but this group chose to only change the music type in their little plant experiment here. So everything else was going to remain the same, so that way for each of the trials they ran, they could try to look for patterns. How are things changing as I change the music type? So music type would be our independent variable here, and our control variables would then be light amount, water amount, plant type. The last type of variable is your dependent variable. This is your data. So this is your dependent variable. It is important to note, like we have said before, data can be in the form of measurements. And shout it out into your room or the void or the library, wherever you're watching this, observations. It is really important to know, I'm going to bring it up a lot, observations are data. They're really, really important in chemistry. We have to look for visual cues to show how things are changing. We have to smell. Odor is a huge one in chemistry. So measurements, important, observations, equally as important in the experiment. So for this group here, their data they collected was the height of a plant, which means that this is their dependent variable. Hopefully you can get these Keep these straight because data starts with a D, dependent variable starts with a D, so data dependent variable. Okay, so let's consider this experiment that this group was running. What's the question do you think that this lab group was trying to investigate? I'll give you a second. Pause the video if you need to. Okay, hopefully you said something along these lines. How does the music type played to a plant affect its height? So, when you are trying to design an experiment, any sort of scientific experiment, you need a guiding question. That guiding question has to have the two most important things. What is your independent and what is your dependent variable? What you're really trying to do is like guide your experiment in a way such that you can pick out a pattern. What is the relationship between two things, your independent and your dependent variable? So as long as you have something written kind of like this in yours, with your independent and dependent variable, you'd be good here. I'm just going to point out music type is my independent variable and my plant height is my dependent variable, just to kind of help me annotate this to keep it straight in my brain. So this is one way that we could organize data in a results table. The other way that we could organize data is in the form of a graph. So we're going to do so much graphing in this class. I am going to force you to know how to graph things by hand, but we're also going to work with Desmos to use a computer to help us format our graphs, make them look nice and pretty, and do a lot of the work for us. But it is incredibly important to me that you know how to work Desmos, and why it works, I guess, is what I'm trying to say. You need to be smarter than the computer. You need to be able to tell Desmos, this is what I want my graph to look like. Here's the function that I want to put in. I know my bounds. It'll scale it for you. It'll make that nice and appropriate, but you want to make sure that you understand what the graph is showing so you can appropriately say, oh, it did it correctly, it did it incorrectly, and then you can use that tool to help you then go through and look for patterns, make interpretations. So we are going to do both by hand and Desmos, but it's very important to me that you are smarter than your computer, so you understand how Desmos works. So we're going to play around a lot with that in this unit and this class. So there's 6 elements to any good graph. I want you to kind of use the mnemonic Sultan to help you out with remembering what would need to go in a good graph when you make yours in this class. So here are the things. First off is scale. You want your graph to take up as much space on the page or on the graph, whatever you're looking at, as possible. And each hash mark also should be equally spaced. You don't want to do start counting by 5s and then randomly start deciding you're going to count by 20s. That's crazy because then each hash mark is not worth the same amount and your graph is going to look skewed. Don't lie to the people. Next up, units. Oh my God, hopefully by now you understand that units are so crazy important. You've known me for 3 weeks at this point. Please put your units. If something is unitless, then you don't have to, right? Like if you're making a graph with year or level or type of chip, whatever your independent variable might be. If it doesn't have units, don't put it. If it does have units, make sure you're putting them in parentheses behind your whatever the actual variable itself would be. Next up is your legend or labels. That's your L here. If you have multiple data sets on one graph, please make sure you put your legend. I'm gonna draw your attention to this graph down here. I'm gonna use this graph again, so we're not actually gonna use it on this page, but I wanted to use it as an example here. This would be this group's legend, the habitat size. So it's showing you that there's multiple data sets that are on this graph. If you have multiple data sets, you've got to put a legend so people can clearly see what the heck's going on. Along with your legend and your labels, you want to make sure if your data points are hard to read or your numbers are really small, you've got decimals written in there, feel free to label your decimal points, or feel free to label your data points. It might make it a little bit easier to read. And then lastly, label your graph with a descriptive title. Please, please, please do not put your title as independent variable versus dependent variable. For instance, with this graph here, they did not put this versus this. Kind of drives me crazy. It doesn't really show that you know like what your graph's actually showing. Like if Desmos were to auto-populate a graph for you, you want to make sure you know what your independent and your dependent variable are. So your independent variable always goes on the x-axis. So here that would be number of rabbits. So I said effects of number of rabbits. This is my independent variable. This is what I went ahead and specifically manipulated in this experiment. And then what did I measure? I wanted to measure how it had an effect on the average grass height in a habitat. So this would be my dependent variable. And you might also be asking, what the heck is habitat size then? Well, habitat size then must be a control. This thing must have stayed the same throughout the experiment. But notice there's 3 different data sets on here, right? So this means Triangle kept their experiment, their habitat size, 150 square kilometers for each of their 1, 2, 3, 4 trials that they ran. So it is still a control within their experiment. Okay, so that's my L, labels and legend. Next up is going to be T for trend line. This one's going to be really, really important in helping you look for patterns in the data. It also helps you when you're making predictions. You can use your graph to interpolate and extrapolate, which is going to be the very last section of this mini lesson, which honestly might turn into a macro lesson. I'm worried it's going to be long. Sorry, love you, bye. Trend lines. One important thing about trend lines is you always want to use a ruler because you want to make sure that your line is nice and straight. You do not need to include outliers in your data. So for instance, if I were going to draw a trend line for Triangle, these 3 I can get to lie so nicely, so perfectly on one line like this, and that triangle down there is completely out of the way. So if I did this, now all my data points are getting skewed, they're getting skewed, not good, ugly. So I'm just going to say that this thing is an outlier and I'm not going to include it in my trend line. But I can take this and I can now draw a line that connects all 3 of these data points really nicely. And when you draw your trend line, you want to make sure you extend it through the sides of the graph so I can use it to then make further predictions from my graph. So trend lines, there's that one. Okay, next up, accuracy. Put your points in the right spot if you're graphing by hand. That's essentially what this one means, which seems like common sense, which is why I put like 40 exclamation points here. But just, double check your work. And then lastly, neatness. I'm going to have to grade these. Please make it legible. If I can't read it, I won't grade it, man. Just keep it nice. All right, so this is your 6 elements of a good graph. What I want you to do is practice. Construct a graph for this data that's presented here on this little template for you, and then you can go ahead and check the answer key. I'll have this posted in the resources folder and on Canvas for you to double check yours. Okay, so part 3, moving on. Once you now have a way to visually represent your data, whether it makes more sense to be in a results table or it makes more sense to be in a graph, this is probably the most important part here. Analyzing your data, identifying patterns. So, what actually is a pattern? A pattern is a repeating arrangement or a sequence of data. So, you take a look at all your numbers, everything you've got. Do you see something that's repeating? Do you see a sequence there? Trends are patterns of change in your data. So this is why they're called trend lines, right? It's more about like how is your data changing over time, or what's the relationship between 2 variables, independent and dependent, as measured on a graph. So what I'd like you to do is get a little bit of practice analyzing data or looking for patterns. I gave you 2 questions here, number 3 and number 4. What you're going to do in this first one is look for patterns in a data table. And then in the second one, you're going to look for patterns within a graph. So you're going to go ahead and pause the video. You're going to work through these 2 problems, and then you can check in with the answer key to make sure you've done them right. But really, this is just getting you to look for what is the repeating pattern, what is the sequence, and then is there a trend in my data? Do I see things going up, going down, staying flat, therefore no trend? all that kind of stuff. So get some practice in 3 and 4, pause the video, and then come on back. Okay, so part 4. After you have analyzed your data, you've got it represented in a really nice way on a graph, you've looked for patterns, you have identified some of these patterns, what do you actually do with it? What we do is we make a conclusion and then we make a prediction. Conclusions must be grounded in your scientific reasoning. There is like some general science practice that either we've been learning about or maybe you know from the past, like we did with the magnets. So that's really going to tell you like, why is your data relevant? Why is it valid? How does it connect to what we've been learning? So here's your basic definition. A scientific conclusion is a claim supported by data, grounded in scientific reasoning. So if I ever say, hey, what's your conclusion? I don't want you to just give me a claim. I don't want you to give me just a pattern. You got to back it up, right? So a claim is a testable statement. And your claim is 1 sentence long. This is really important. Some people try to give me like 40 lines of claim and it just gets crazy. It is 1 sentence and it contains the pattern within your data. Pattern or the trend within your data. So what do I mean by testable statement? It means that it was something you were able to design an experiment around. I'll kind of show you how it works when I do an example here. And then again, data can be collected in 2 forms. We got measurements and we got observations. Lastly, your reasoning. So your reasoning is your basic scientific concept, like I said earlier, and it ties together your claim with your data. So essentially, it proves why your experiment is relevant and valid. So remember, we did a lot of practice with this in Unit 1, where we wrote like our CERs, our claim evidence reasoning statements. That can kind of be consider your conclusion. But remember, we don't write them in that order. I know I'm presenting the conclusion as a claim supported by data, but this supported by data is the more important piece here. This should always be number 1, which is why I was calling them an eker for a day, right? We want to start with our evidence. Our evidence is the thing that drives our claim. So let's take a look at this results table here. So I'll give you a second, just kind of orient yourself. What is this results table showing? Okay, one thing that I notice is that this group decided they're changing their independent variable, their changing variable. It would be the light amount here. This is what they physically manipulated. They chose to intentionally manipulate in this experiment. They held the water volume and the soil type constant in this experiment. And the data they collected, they got some information about plant height, a measurement, and then they made observations. Okay. So, is it possible for this group to make a conclusion? What I really mean by that is, do they have an independent variable and a dependent variable? And do they only have one independent variable? The answer is, yeah. I only changed one thing in this group. I changed the amount of light. Everything else was held constant, and I did collect data on this. So yes, I can potentially make a conclusion. So, let me give you possible claim. I'm purposefully living... Oh, possible claim and reasoning. This should say possible claim and data. Silly goose me. So I'm purposely leaving out reasoning because this is biology. So you can learn more about this next year. I guess I probably should have chosen something physics related, so that way we could have done some reasoning in it, but oh well, you live and you learn. Okay, so possible claim and data. When the light amount was level 0, no light, the plant height was 8 centimeters, and when the light amount was level 5, full light, the plant height was 4.2 centimeters. Therefore, we can claim that the greater the light amount, the taller the plant height. So let's break this down. Do we have data present? Do we have measurements or observations? Okay, well, I see level 0 light and 8 centimeters. So this, actually I shouldn't box that. This 8 centimeters is data. This is information I collected, and it's tied to the level 0 light, which was the independent variable for that trial, the independent variable value for that trial. Level 5 light is connected to 4.2 centimeters. So there's some more data that's presented right there, 4.2 centimeters. So this is a data statement. It contains a connection between an independent variable value and its dependent variable value. So now we double check, does this match up? Level 0, 8 centimeters, level 0, 8 centimeters, that looks good. Level 5, 4.2 centimeters, level 5, 4.2 centimeters. That looks good. Okay, so our data statement's looking totally fine. We have our independent and our dependent variables. They're connected correctly. Now we move next. Therefore, we can claim, okay, so I'm seeing this now. We can claim the greater the light amount, the taller the plant height. So stop and ask yourself, is this a testable statement? Does it contain an independent and a dependent variable? Does it contain a pattern? The greater the light amount was our independent variable. The taller the plant height was our dependent variable. So step 1, it does contain independent and dependent variable. It is testable. Now we check, does our claim make sense? Okay, the greater the light amount, the taller the plant height. The greater the light amount, the taller the plant height. Uh-oh. This doesn't seem to be matching up. Our claim and our data aren't matching. What we're seeing is as the light amount is increasing over time, the height of the plant is actually decreasing over time. So is this a correct conclusion? No, it is not. It does have a data statement. It does have a claim, but they do not match each other. So what's wrong with the conclusion? Claim doesn't match data. So ask yourself, can I fix this? Is this an easy fix or a hard fix? Do I have to run an entirely new experiment? Well, no. There's a pretty easy way to fix this one. All I have to do is say, the greater the light amount, the shorter the plant height. So my reason for choosing this one, my reason for choosing it this way, is that if you were going to try and fix a conclusion that's been given to you or that you're trying to write here, you can always change your claim to match what your data says. In fact, you should change your claim to match what your data says. You can never go the other way around. I can't say, oh, well, that's confusing. It doesn't really make sense to me. So I'm just going to like swappity swap these things here. And I'm going to say, oh, actually level 0 had 4.2 centimeters as their plant height. That doesn't work, right? You always go with what the data is telling you. Even if it doesn't necessarily make sense to you at first, maybe that just means we could have done something incorrectly in the experiment. Maybe we should run the trials again, see if there was experimental error, all of that kind of stuff. I will tell you for this one, this is not experimental error. This is realsies. Okay. So, very last thing. You've run an experiment. You've put your data in a usable way in a results table or in a graph. You've analyzed what that data is. You've looked for patterns. You've come up with a claim supported by data, grounded in scientific reasoning. What are you going to do now? Your last step is making predictions. Science experiments are never really over. I know that's kind of a crazy thing to say because you're like, what? What do you mean? I have to keep doing this experiment a million times? Not necessarily. What I mean by this is that you can always use the data that you get from an experiment to make further predictions to guide future scientific research. You should never be complacent, right? I can learn something and then I go learn more about this thing. That's really what scientific research is all about. So the last thing, the last thing that we would do from a scientific experiment is make predictions from our data. And this is where these two words that I talked about earlier come into play. Extrapolate and interpolate. So these are really key for when we are using graphs, data in graphs. To interpolate a value means to estimate a value that's between two known variables. Hopefully this kind of makes sense because the word inter, or the prefix inter, really means between, right? So inter is between. Extrapolate, prefix extra, means literally like extra on top of, right? So this would be to estimate a value based on extending a range of known values. So if I've got some decent data, I can extend my range of known values in order to make further predictions. So you're going to practice this skill by using number 6. One thing that I want to point out, this is the same graph that I used up here, so I'm actually going to go back to this one to draw on it really quick because I've already drawn my trend line. So one thing about interpolation is that it's between data points, right? So say I wanted to interpolate, make a guess about the average grass height if I had a number of rabbits that was, say, 22. So 22 falls right here. What I can do to interpolate a value is I can use the trend line that I've created to make an estimation based off of all of the other data I've collected. So you do need a ruler again for this part. What I can do is simply take my ruler and lay it on my graph. First, I want to lay it vertically so I can trace up to where my data point meets my trend line. So I'm trying to make a prediction at 22. So I'm going to follow up to my trend line where it would hit at 22. And then I'm going to turn this and I'm going to lay it flat now, horizontally, and I'm going to trace back to the y-axis. If I trace back to the y-axis, now I land on approximately 37 as my average grass height. So if I were to say, hey, what would the average grass height be in a 150 square kilometer habitat when there are 22 rabbits, I can use my trend line to interpolate that data. Extrapolation would be the exact same process. The only difference is now you're making a guess that's outside of your range. So if I wanted to make a guess about the average grass height in this habitat with 5 rabbits, I'm now outside my data range because this is where I collected my data. The other option would be if you needed to make a new trend line, you can totally do that. If I had 2 data sets here, my triangle and my square, and I wanted to make an estimation about the average grass height if I had a 125 square kilometer habitat, this is another way that I could do extrapolation. I could make a new trend line that sits between my other trend lines and use that to make further predictions, which is what you're going to have to do for one of the questions on that last page. So take some time, go through that last page, see if you can make some predictions, check in with the answer key, and then we'll do more practice with this in class, okay? Bye.